What up, athletes? All right, we're doing this again. This is day 2 of talking about the perpendicular bisector theorem and the converse of the perpendicular bisector theorem. And we talked about in day 1, we had that kind of launch the lesson video, which was talking about 3 towns that raised money to put a pool. And they wanted that pool, because they all 3 contributed, they wanted that pool to be equidistant from them. So we talked about how we could make a triangle out of the 3 things, and the perpendicular bisectors of those triangles found us the middle. Well, today we're going to talk about that. So I'm going to do a little activity right here and try to move my video out of the way. It tells us a perpendicular bisector is a line, segment, or ray that passes through the midpoint of a segment and is perpendicular to that segment. We're going to use the sketch to explore perpendicular bisectors and triangles. And you guys can also access this, by the way. I want to take a minute and talk to you actually about how to access this. So let's explore that. Right here, I'm in Connect Ed. So I'm going to go back a little bit. You guys should know that if you get into your Canvas page, right? If you get into your Canvas, on that upper left it says Connect Ed. If you click on Connect Ed, it'll take you to this. Now, you'll only have 2 options. You'll have an Alex and you'll have your math book. And your guys' math book actually looks like this purple thing right here. You really don't need to go in this much unless you want to look at extra examples and things. But if you ever want to look at some of the slides I go through, I add them to your calendar and I'll show you how to access them. So you would just go, let's say if you're my period 5, you would go into period 5, or your math book. It's going to take you to a dashboard that looks similar to mine. And I've actually, I should have added it on the calendar. It should say, it's because I'm not there. That's right. If I go, look at that. If I go to next Monday when I'm actually going to teach this lesson, on your calendar it's going to say this. And you can click on that now. If you hit view, it should take you to this right here, if it ever doesn't, because I've had times where it's not worked as it was advertised. What you can do is, we're going to be starting 1-1. You can click up here where it says, where do you want to go? Browse course, click that drop-down arrow. We're going to be in Module 1. Click that drop-down arrow, and we're going to be in Lesson 1. It's going to take you to the same page. So those are 2 ways to get to it. And then you won't have all my bells and whistles right here. You'll just have launched the presentation. But you can do that to access the same slides I'm teaching from right here and be able to utilize them to help you. And you can play with some of this stuff in here that I'm about to show you, which I think is awesome. So yeah, this was our warm-up from yesterday, or whatever other day we did it together, depending on when you're viewing this. And let me go over here. We should be right here. All right, we're going to be talking about doing an activity with perpendicular bisectors. Good times. All right, this tells us, and you can do this on your own. I'm going to do it for you guys, though. It says, step 1, press the triangle button. I'm going to press that. See how it makes a triangle for me? Now, to get it to stay, I need to actually touch each point. And once I do that, make whatever triangle I want. It doesn't matter. You make it however you want to make it. Now, we're going to press the perpendicular bisector to construct a line that is perpendicular to AC and bisects AC. So, see, I press that, and I'm going to take this point, and I'm going to drag it onto A. I'm going to take this other point and drag it onto C, and this has created a perpendicular bisector. This line that I've created is perpendicular to AC, and it cuts it in half, so that we know that the distance from A to this point, we'll call it D for now, is congruent to CD. All right? Now I'm going to erase that so you're not going to see the tick marks of these, but I want you to understand this is what I just did. Now the directions then tell us press point D and plot a point on the line perpendicular to AC, but not on AC. Construct and measure AD. Well, we're going to get that. So first, I'm going to make a point D. I'm going to drag it, and I want it on this line right here. So I'm just going to drop it there. Once it highlighted red, we know it was on the line. Now see this segment right here? I'm going to draw a line. And see how it has a name, EF? Well, don't worry about that. When you drop it on A, we're going to drop it on D. Watch this. It becomes AD. See how that works? And we're going to construct one on CD. Drop that on C. Kind of snaps to it when you get close to it. Now I've got CD. Now here's what's cool. Notice this is giving us the measure of AD is 7.62 centimeters. The measure of CD is 7.62 centimeters. Watch what happens to the measurements as I move them. They stay the same, don't they? Because I'm on that perpendicular bisector, what does the perpendicular bisector theorem tell us? It tells us that the distance from the endpoints of the bisected segment will be equidistant from each other. Anywhere on this bisector line, if I can go down, it's still equidistant. All right? So, let's go on to the next set of directions. Now we're going to slide point D along the perpendicular, and I just showed you that, just what I showed you. These measurements right over here are always the same. They do not change regardless of where I put D, where it's located, as long as it's on this perpendicular bisector. If I were to pull D off, it would change. Press the arrow button, all right. Boom. Then construct a perpendicular bisector of each side. Okay, so here's what we're going to do on this one. Now we're going to do more what we talked about with that swimming pool problem from day one. Watch this. And this is really cool. I like working with this. So I recommend getting these slides, mess with them, have fun with them. Okay, I'm going to actually make 3 perpendicular bisectors. And I try to orient them as best I can. There we go. There we go. Get them right on there. Now, you notice there's a point right here. And we're going to talk about that point. That's really what these directions are going to tell us to do. It's going to have me create a line or a point right now. When you do this, you got to do it so that it contacts 2. I know it should look like it contacts 3, but as long as you do it on the 2, it's going to count for the 3rd one. I don't know why this does it, but it does. So if you go to do this on your own, and we're going to construct 3 different lines here. Watch this. Again, as long as you drag them on the points, they just become that line AD. Now I'm going to create BD. And I'm going to create CD. Notice that I have measures over here now. I have the measure of AD from A on the triangle to D, measure of point BD from B on the triangle to point D, and the measure of DC, which should really be CD, but I guess it doesn't matter, which is, again, from C to D, same thing. Check this out, though. If I move this triangle, right, notice all these measures are the same, because wherever these perpendicular bisectors connect, wherever all 3 perpendicular bisectors connect, will always be equidistant from A, B, and C. Watch this. I'm going to move A out. Now notice it's changing the location of my perpendicular bisector, which moved D, but because D is moving with it, we have it locked to the 3 perpendicular bisectors moving in one. Notice the measurements. Oh, you can't see, I'm pointing the screen. Notice the measurements over here where my mouse is pointing. No matter what I do, because D is locked to the point where those perpendicular bisectors meet, the measurement stays the same. It's equidistant. So this is how you find, if you want to take something and find out how to place it in a point that's equidistant from other points, this is how we do it. We use the perpendicular bisectors. I think that's pretty awesome. So we have some exercises here. No, we're not going to go through those. These are pretty awesome. I like exploring little geometry deals like that. I'm a math teacher, what can I say? Even if I wasn't, I like that stuff. I like puzzles. These remind me of puzzles and little logic puzzles, so those are fun for me. So perpendicular bisector of triangles is what we were just talking about. And when 3 or more lines intersect a common point, the lines are called concurrent lines. So I want to make sure you understand a little vocabulary here. Have this written in your notes. We'd have concurrent lines, and what are concurrent lines? 3 or more lines intersecting at a common point. Okay, have that vocabulary. Now, we also want to know this vocabulary word right here, point of concurrency. The point of concurrency is the point of intersection of concurrent lines. Okay, the point of intersection of concurrent lines is the point of currency. Make sure you know that. And then a triangle has 3 sides, so it also has 3 perpendicular bisectors. These bisectors are concurrent lines, right? Because they all bisect in one point. And remember, where 3 or more lines intersect is called a concurrent. They're called concurrent lines, and that's a point of concurrency. So at that point of concurrency, the point of concurrency of the perpendicular bisectors is called circumcenter of a triangle. So the circumcenter of a triangle is what? It is the point of concurrency of the perpendicular bisectors of the sides of a triangle. I told you there'd be a bit of writing today. Take a minute, write that down. Well, I said it yesterday, or the other day we taught first day one of this lesson, but there's going to be some today. And we have another theorem we're going to go through. So pause this if you need to, write it down, then let's move on. This next theorem is this, and I do want you to draw this picture. And once you draw it, please make sure you also, so we're going to write down theorem 6.3, circumcenter theorem, and then I want to write this down. What is it? The perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. All that means is point P is the same distance from A, B, and C, which are the vertices of the triangle. A vertex of a shape is just that, right? Like we're talking like a pentagon. The vertexes are the points where lines meet. Okay, and the last thing I want you to write down is right here. So for this example, if P is the circumcenter of triangle ABC, then we know that PB is equal to PA, which is equal to PC. All right? We know that all three of these lines, that was terrible. Oh, it's still terrible. Imagine they were on the lines, are equal to each other in length. That is the circumcenter theorem. Again, write that down. We're going to go down here and look at the proof of this theorem. So we're going to start getting into proof territory. I don't know how much we're going to do of those in the coming weeks, but you are going to see proofs. So the perpendicular bisector of AC, perpendicular bisectors of AC and BC meet at P. Right? That's the point they meet at. We want to prove that these lines equal each other. Here's how you would prove that. First, because P lies on the perpendicular bisector of AC, right? Perpendicular bisector of AC, it's right here. Then we know that these two lines are equal to each other. We know that by the perpendicular bisector theorem. Perpendicular bisector, basically we're just also saying this line, because it lies on the bisector of BC, we know that these two lines are equal to each other. And because it lies on the perpendicular bisector of, oh, no, we don't need to go further than that. That's right. By the transitive property of equality, we can then say AP also equals BP. Because BP was equal to CP, and we know CP is equal to AP, therefore we can say BP is equal to AP. Okay? All right. Now they're all equidistant from each other. So thus, we can prove that AP equals CP equals BP. Because AP equals BP, the converse of the perpendicular bisector theorem tells us that P is the perpendicular bisector of AB. Now, that may wash over your head. Maybe you're starting to understand it a little bit, but I'm going to continue kind of reading you through some of these proofs and talking through some of these proofs, and eventually we'll even do some of these proofs. It'll be exciting. But that is how we know that this theorem is true. Proofs are a way that we prove something is true, and then we can make a theorem, and we can say in the future, especially if we do it for a variable, then we know it's true for all numbers that we could plug in for that variable. Awesome. So we're going to use the circumcenter theorem right here. And I better move my video out of the way. I'm so sorry. So it says find FL. So what do we want to find? We want to find FL right here, this distance. If H, so we know that H right here is the circumcenter of triangle EFG, this big triangle, right? This whole big triangle. And EH equals 4.85, okay? So we know this distance right here is 4.85, and LH is 2.28. Well, here's what I do know. If this is the circumcenter, then I know that GH, we're trying to find what, LH? Oh no, FL, excuse me, FL. So if this is 4.85, I also know this is 4.85. Right? FH is, because we know by definition of the circumcenter theorem, that EH, GH, and FH are all equidistant from H, or the same length, right? So E, F, and G are equidistant, which makes those lines the same. So I can just say, hey, FH is 4.85. And guess what I've just made? Did anybody see what I just made right here? Isn't this a right triangle? So if I were to redraw that, this would be point F, this would be point L, and this would be point H. And I know that LH is 2.28. And I know that FH is 4.85. And here's what I also know. I know that A squared, why do you think we did Pythagorean theorem the other day, plus B squared equals C squared. Now, if I'm going to call this A, B is what I'm looking for. So I need to solve for B. So I'm going to subtract A squared over and take the square root of both sides. And when I do that, I'm going to get that B, because the square root of B squared is B, is equal to the square root of C squared minus A squared. Which C is my hypotenuse, A is 2.28. So I'm going to get that FL, in this case is B, right, is equal to the square root of 4.85 squared minus 2.28 squared. Now, if you do this on a calculator, which I just did, sorry, I paused it, was going through it, this is approximately, I'm going to round it to the hundredths. Because all these are in the hundredths, I'm going to round to the hundredths, and it becomes 4.28. And let's look at that. Oh, I see 4.28 is an answer for B. So I'm about ready to erase all this. Are you ready? Going, gone. Put in our B answer. Hey, look, we did it right. Awesome job. Got to reset activities the next time I present with this. That happens. And let's go ahead and go on to the last thing we're going to do for today. We're going to use it in a design problem. A work triangle is a design concept used to create an efficient kitchen layout. You can use a work triangle to reduce the number of steps it takes to walk between the refrigerator, stove, and sink. If a designer wants to create an island for the kitchen, shown where should the center of the island be located so that it is equidistant from the refrigerator, stove, and sink. If it is necessary, round your answer to the nearest hundredth. All right, well, let's take a look at this. I'm going to come right here. Here's where the triangle's laid out. And let's see. I'm going to make my perpendicular bisectors, right? S. I'm going to make a perpendicular bisector of R and T. Perpendicular bisector. I encourage you guys to go on and play with this in the slides. It's kind of fun. R and S, we see a point right here, P. And where's that point, P? Okay, so we want to make sure that's at the right spot. All comes out right. Where do we see point B? 8.5, 8.5. So we want to put the answer down here. The coordinates of the island should be at 8.5, 8.5, 8.5. And we proved by putting in the measurements that it is equidistant from RTS, which represents our work triangle up here of the stove, sink, and fridge. Awesome. That's what we're doing. Boom. 8.5, 8.5. That work triangle is a real thing. McDonald's. The guys who created McDonald's actually used this type of math to create McDonald's in such a way that workers, almost like a ballet in the original McDonald's, would work around each other in a very small area, never hitting each other, and able to work at a speed that previous to McDonald's doing this had never before been seen at restaurants like that we now call fast food. They used to be not that fast. They used to be like a 15, 20-minute wait, and then they cut it down to like a 1 or 2 minute wait by what they were doing. It's pretty amazing. There's a movie called, I think it's McDonald's Inc. or something like that. Excellent movie. Anyway, all right, with that said, peace out.